Hello, everybody, and welcome back to a new episode of this series. So last time we've started work on our physical memory manager, and we've filled in all the necessary for allocating physical pages. We still haven't tackled freeing them, but that's a problem for future me. So today I want to take a look at least putting in place a setup for virtual memory management and page allocation. So we are going to do just that. Let's get started. Right, so the only thing that's different from where we left off last time is that I've moved this PMEM module here under the memory folder, just so that we can have all the memory stuff nicely grouped together somewhere. So let me just add a vmem.zig module here, and we will see where we go from here. And let's get to it. So I'm pretty sure we are going to need stud, so let me just get that. That should be fine. So let's first of all think about what we need for virtual memory management. Okay, so let me go back to the, I believe it's the BIOS stuff, and here let me just open these. Oh, those are some nice graphics. So let's see here. We had this page map struct, and then we had, so all of this is for kernel stuff. Let's see if we had something here. So we had quite a few helper functions to map physical addresses to virtual addresses. So we would need to have those too. And I guess that's pretty much all we did for virtual memory management. So yeah, sure, okay. So let's create a public struct. I'll just call it page map. And this here will have pretty much the same structure that we had. Actually, if I remember correctly, in the UEFI bootloader, we also had this page map struct. Did we not? Oh, so it was called address space, I think. Yeah. So this was it, actually. Yeah. Okay. Cool. Right. So as we can see here, we had just the root address of the page map, and then the number of levels we had on it, and a few functions to map physical addresses to virtual ones. Right, so let me just create that again. Right, so wrong language. Wrong language there. So const page map is struct. Yeah, I was wondering why it was highlighted in red. This is not crablang. Right, so we want a root, which would be a U64, just an address. And we want the levels, which would be, I guess, just a U8 would do. And let's leave it that for now. Let's also create a const, so virtual memory manager is a struct. And actually, I want to double check what we did here for physical memory. So we actually had the manager here, and then we had in the module itself other functions that interact with the manager. So let me think about this. yeah, now that I see this, I'm not the biggest fan of this way of doing things, especially since we are going to need both modules, so pmem and vmem to interact. I believe I've put a comment somewhere. There we go. This here. So we'd want to virtually map memory regions or physical memory regions to write to them. So if we want to zero them out, so we are going to need to have both of those interact. So what I'm thinking right now is extracting this functionality here, all of these functions, or all these functions that we have on the module itself, to a separate module that I'll call, actually, let me just go ahead and create that module here, memory.zeg, and this module here will so have pmem is import memory meme ori meme. Okay, I swear I'm not doing this on purpose. So let's do this with this, and that should do it. And this module here will be, this module is the entry point to everything memory related. And let me just not to do move all interacting all functionalities that interact between pmem and vmem meme here. Right. Right, so now that we have our virtual memory manager, let's actually, I'll be a bit lazy and just go ahead and copy paste some things. So this we'd want, this we'd want. All of these we don't want, but I'm still going to take them. And let's go here. We need to import that, so const spin lock is, I believe that's in synchronization.zeg dot spin lock. Yes, spin lock. Right, and of course allocator. Not sure we are going to need those. These would be vert. These would be vert also. This would be vert. We are not going to count total memory. We are not going to count reserved pages or uncommitted or committed pages, because we don't have those notions. Those concepts don't exist in virtual memory land. Spinlock we want. Here the init will not take anything. We don't have an allocator. We are not going to have any of these. Right. That's very, very nice. So just going back to pmem for a quick second, we are going to take, sure, we already have, sure, that's pretty good actually. We already have the formatting stuff for that, so I'm not going to say no. So let me put that here. This would be a v address. This is going to become a backed struct backed by EU64 that we are going to define in a bit. Right, so this one is a v address, and this one here. So it is going to have a type. We are going to want to type this, the v address ranges, but we are going to do vert range type. Sure. This would be an enum. Do we back it by something? I don't think so. And I'm just going to say that it's unbounded. Does it need? Okay, so it needs an. How many types do we expect to have? I think U8. U8 would give us 256 types. Yeah, sure. I'm not sure we are going to need all of those, but for the moment, let's say we are okay with that. Yeah, vert range type. And actually that tells me that the other side here, memory range type, is probably not well named. So let's see here. Let's call this phys range type for now. Cool. So we have a start, a length, and a type. The only problem is that we are not going to be able to use tag name for the type, because we may want to define our own types afterwards. Well, it's an unbounded enum, so all the tags will not have names. So how do we go about this? Let's int from enum, I guess for now, is as good a solution as any. Right, so now that we have this, we can actually let's change this to need to be vert. Oh, we not rename this. Cool. Vert. Let me just do this. Phys goes to vert everywhere. Of course, we are going to need to import our list. So doubly linked list, sure, is import. Again, I think it's in list.zeg dot doubly linked list. Sure. Okay, so that works. We are not going to need memory ranges because pretty much all the memory is available, I think. Yeah. Now, what I will need to do though is have public function add range or register range. So I want to use this function here to decide which ranges to, because we don't have a virtual memory map. So we decide which regions should be available and which should not be. And I think this register range here would need to be that vehicle that lets us decide. So here we are going to take, we could take a virtual memory range as input, but I would rather take just parameters. So let's think. We would like to have, well, first of all, we'd like self, which is self, maybe a pointer to. So yes, we are going to change things, and then we'd like to have, and of course this language here, so register range. Yeah. Okay. So self, and here it have a start. Let's start with a type, I guess. So this one would be so vert range type. Range type. Then we can get start, which would be a U64, and a length, which would be U64 also. Sure. And here we can return either an error or void. So what's the, okay, unused, that's fine. And the idea here is, for now, I'll just comment out the things I'd like to do. So also there's another thing I want to put in here. Let me take arguments, and this would be a struct of type, or just a name struct that would have reserved, yeah, sure, as a boolean that defaults to false. Okay, cool. So let me just do this. Which one was args? I guess was complaining, and all the other ones. Type and start and length. Sure. I think this is probably the worst feature of Zig, and it's just going to get worse. The unused argument stuff. Right, so here we have register range. I'd like to, if reserved is true, let's just go ahead. If reserved, add range to reserved ranges. Otherwise, add it to free ranges. Right. And now that I think about this, I want to have, so we can have different page maps. We can have a page map for kernel, for the kernel side. We can have a page map for user side, and we can actually have any number of page maps we'd like between those. So I think every single page map would need to have its own virtual memory manager that would track which parts of the memory are mapped to which parts of physical memory. Or rather, it's the other way around. So which parts of physical memory are mapped to which virtual addresses. So here I'd like to add VMM, which would be a virt memory manager. Sure. So let's think about this. So after registering ranges, another thing I'd like to do probably is have a function that invalidates the TLB. Yeah, so this one here would just take a self. So let me think about this. We are going to want to invalidate an address range, or one or multiple address mappings. So those would be pages from the TLB. So I guess we are just going to go for address, and that would be U64. For now, let's just keep it fairly broad. This would return nothing, and can I have some of that? Apply fix all. Cool. Right, and here, so there's I don't remember the actual assembly instruction to use, but it's invalidate something like so. Yeah. So call instruction to invalidate the TLB cache for address. Right. So now that I think about this, let me just backtrack here. So I think we are just going to do this, have this be So const self is this. So this would be a module, so a file level struct. Ambiguous reference. Yeah, let me just do this. Sure, this should work. Yeah, this is kind of shitty, but actually, let's leave that be. Yeah, that should be fine. And let me just remove this here for now. So here's what I want to do. Actually, this one here, since it's going to pertain to pretty much all the pages, and we're not going to need any self. So we're just going to call an instruction on an address. We can just have that floated here. It's not public, so it's fine. And actually, I want all of these to act through the page map. I want the page map to be my access point to all of these functionalities, if that makes sense. Also, I'm just going to note that here, this is used for init initialization only. So maybe to do check that it's not misused. Yeah, sure. Let's say that, and then here I'll have another function. I'll call it reserve range. That takes a self pointer to this, takes a type, which is a vert range type, start u64, length u64, and of course we are going to reserve that. So here we can return the same thing. So this one here reserves a free range. So basically moves the range from free ranges to reserved ranges. No, there we go. Cool. Let me just, of course, this wrong language again. What did I call that? Reserve range. Yeah, and fix all. Cool. Right, so here we are starting to see what the API would look like for this virtual memory stuff. I also would like to add so public function how am I going to call this? Allocate range. Sure. And here I want to have args at the end, which would be a struct that's going to tell me from which type. Oh, hold on 1 second. So I'm going to ask for a length, basically. And of course here we need self to be a pointer to, oops, there we go. And for now, let's do this. So I want to allocate a range, and I want to specify if the range I'm allocating is from a free range, so from pretty much anywhere, or from some specific range that I've given a name to. And actually, now that I think about this, does it make sense to have a, let's call this any, have this be any, yeah. And let's think about this. So instead of having this reserved here be a Boolean, we can actually have type here be vert range type, an option on that, and for that to be null. Yeah. Okay. So if type is set, then it is a reserved range, since reserved ranges would have types. And basically what I mean by that is I would like to have a range that's reserved for frame buffer. So I want that range to be from here to there. Okay. Does not mean that the frame buffer is using this whole range, but if I want to create a double buffered frame buffer, I'd like to reserve my first buffer here and then my second buffer here within this same range. So that's what I mean by reserved ranges, and this range here would have a type of, let's call this frame buffer. Yeah. Same goes for MMIO. So if I want memory mapped IO for something, so for accessing devices or stuff, I'd like to reserve a range in memory for PCI bar and stuff like that, and then call that MMIO range. And if I need to allocate a virtual memory that has to do with MMIO or device stuff, I'd like to allocate within this range. So that's what I mean by reserved range. It's not reserved in the sense that it's already used. If it's the case, then we will not have it in the range. We are going to carve out slices from that range and return them. So we are not going to have any used ranges in our reserved range list. We are going to remove them. But this is what I want to do. But in the free list, I just want to have all the bits of memory that remain. But I don't really need to give them a type at all. So yeah. And actually, let me just go back here, and I'm just going to remove this because yeah, we don't really need a type of any. We are just going to remove that and replace that by null. That sounds pretty okay. I think. So maybe here we can go ahead and change this to any, just to avoid any surprises. Oops. Yeah, not really what I wanted to do, but okay, fine. Okay, so now this means that I can do pretty much the same here. So type, which is a vert range type, which is null. And this means that if this type here is null, I would like to allocate this range from the free list. Otherwise, I would like to look for this range type in the reserved range and allocate length from there. And this reserve range will pretty much do the same thing. So it will go to free range, look for range that's a range that starts at start and has length to length, and then move it to reserved range and give it this type here, which is why the type here is actually a not optional. And let me just go ahead and put this at the end there. Cool. Right, so here let me just do the fix up here for the unused stuff, and so allocate a range either from free ranges type is null, or reserved ranges. There we go. Right, and actually now that I think about this, either reserves a free range or create a new reserved range if it doesn't exist already. Oops. Right, so that's pretty good. Actually, this one here would return a virtual memory range. Yeah, sure. And I guess we also need so free range, which should take self pointer to this, and well, I guess a virtual memory range. So so here we have a problem. And the problem is I would like to ensure that this virtual memory range here is basically released by whoever has it and calls free range on it. But since we don't have move semantics here, I can either bundle up the free operation inside it and have a sort of destroy function, sort of method that would be called and that would actually call us back, call back this module here to free it. But that's too much work. Or we could just do this and should I add the gridded is valid field? I'm not going to do that for now. Yeah, for now I'm just going to note as a warning, we take a pointer to range, but we can't be sure the owner has how do I formulate this? We can't be sure that the owner has finished with it. Can cause access issues. Right, so if we have a page fault after we free something, we know where to look. Right, so now that we have all of this, let me just remove these comments here. Now that we are set up for basic stuff, we are going to start looking at more advanced stuff. So here's the problem that we have. We are going to, if I go back to pmem, we are going to be needing to do this quite a bit. And by this I mean mapping a physical page, writing to it, and mapping it. And if we go the classic route of doing this, if we go back to our UEFI bootloader, so a map here, this is our function that takes a virtual address and a physical address and maps physical to virtual. And we can see that it does quite a bit of work. So it goes through and checks that all the mappings are created. If it's not created, it allocates pages, writes the entry to the page, checks that the next level exists. If it does not, then we go back here, we allocate page potentially and write to it, etc., etc. So it's quite a bit of work, and it can get really slow, really fast if we do this number of times. So the idea here is we want to avoid that at any cost. And for that, I'm going to create a set of functions. Let's call them quick map as opposed to a map. And this would take pointer to this and a page aligned address. For now, let me just use just generic types, and we are going to fine tune this afterwards. So we want to quick map this U64 address, and we want to return a U64 virtual address for it. And there's obviously the quick unmap equivalent that would basically do the opposite. So it takes the address and just unmaps it. This one is void. Right, so we already know that we have this thing called PML4, which basically dictates how we can map a physical page to a virtual page. So we have 4 levels of indirection, after which we can write our page to, say, for example, that this address here, so 0x123, for example, 134, is mapped to some virtual address that's dictated by the sequence of IDs we've chosen here to go through in this PML4 hierarchy. Right, so that means that in the best case, in an ideal world, what I could have, so I want so this is my quick map. Let's call it QMap. We take an address. This one is a physical address, so let's call it phys for now. And in an ideal world, I would just return a known fixed virtual address, so 0x vert, for example. And here, I need to map adder to vert, right, to this 0x vert address that we have here. But as we've seen, this mapping here, this mapping logic, we need to go through all of these levels here to get to where we want to be, and then do the mapping, etc. But here's the thing. If we say that this virtual address is fixed, that means that the place where we need to map our physical address is also fixed. So if we, for example, know the address of this page here, onto which we write our page table entry, this one is PTE, then we basically just need, this mapping here would just need to be, we write address to this field here, and then we invalidate the page table cache or the TLB cache, and we return vert address. And this would be quite a bit cheaper than just having to map our address to a brand new virtual address every single time. Right, so let's make this a bit clearer by doing something. So I'm just going to go ahead and copy. I think we have, it's just not in a map, it's in address space, write entry. Yeah, sure, but give me the function. So it takes flags, a physical address, and an entry to write to. And hold on, let me see here where we use it. So the entry is this. Yes, okay. So page table mapping, so page table entry taken from the mapping with the page table index from the virtual address, and we write to that. So if I just go ahead and just copy this, just for the sake of making this a bit clearer, just going to put that there. So for now, instead of having this entry here, I'm just going to consider that this entry is an address. Should I do that? I don't think so. No, actually, let's go back to address space and look for page entry, page mapping entry. Actually, we are going to need this exact thing. So let's just copy that also. Let's put it somewhere here. For now, I'm just going to use this as my scratch space. So constants is import constants.zig, obviously, and we don't have arc page size. I think we have arc page size. Right, and I guess we have PML4 virtual address, and we've called that just vadder down here. So let's call that vadder, and read write is undeclared. So let's go back here and get all these nice things. There we go. So cleanup will have to come after this, but for now, let's just move on. Still have some things to add. So const log is still log scoped, and the scope would be vmem. Sure, why not? Yeah, I can't find anything better than that. Right, so now that we have all this, we can go down here, and just to illustrate what we want to do with our quick map. So before we return our address, we'd like to do something like entry. We want to plug in an entry that we already know. So we would like to do something like const var entry is, for now, let's just do this, pointer from int, and we do self dot quick map, yeah, sure, page table entry, dot start, sure, why not? And here we can do entry, and of course we have address, and in flags we'll just do default flags, sure. And here we can return self.quickmap.start. Is that fair? I think that's fair. So this one would have a known result type. Let's give it a known result type. This would be page mapping to piece.entry. Right, so variable is never mutated. Sure, the pointer is not variable. Cool, so this would be a quick and dirty implementation of QuickMap. Of course, we still need to define what this QuickMap PT entry start and this QuickMap start here. But let's actually do the same thing over here. We don't need to return anything. We just need to go over here and do. So we would like to unmap. So yeah, since we only have one entry for now, let's just map that to address 0 and here map this to. Do we have, how do we set flags? They're all set. And do we set present to false? That's very good. So that's all I needed to know. So this can be considered a quick and dirty way to implement. Quick and dirty way to implement this quick mapping and unmapping mechanic that we like. But now that we have this, we are still going to need to define what this quick map page table entry is coming from, or what it is and where it's coming from, as well as this quick map.start. And before we go about doing that, I would like to also make sure that so this would work, but if we have a multi-processing, multi-core system that's firing on all cores, and all cores try to quick map something, this here would cause problems. So there are two ways to solve this. Either we hold the lock, so hold self.lock, think, and with a defer, unlock, or another way to go about this is to actually have one quick map entry. Actually, it's not going to solve the problem entirely, but it's going to mitigate cores having to wait on one another. So we could have as many entries as we have cores. And here we can imagine that we have something like const CPU ID, which would be get CPU ID. And this here would return a, let's say U64. And we can do something like times whatever size of entry, so page mapping entry, and rather this would be plus, and this would be times CPU ID. So we can imagine something like this, and this means that every CPU would just have to basically contend on accessing this quick map with itself, rather than having all our cores waiting for one another to access this quick map. So for now, I'll just not use this, but I will provision enough quick map page table entries and quick map ranges here for all CPUs. And that also means that we are going to need to go to constants and add const max CPUs. Actually, I don't know how we call that here. Max CPU, okay. So let's set it to 8, and I'll need to note actually this needs to be to do because it's fairly critical. Make the max CPU the same for UEFI, for bootloaders and kernel. Idea is take it from Zig build config. So I think in Zig there's this thing here that's called config. It's under stud.config, I think, or stud built-in configs or something. Let me go here. If I do stud dot built-in dot yeah, well, it's somewhere. It's somewhere. I know that it's somewhere. So and we can actually pass configuration to Zig through the build system here. So if I go to, I don't know if it's on the module itself, add config, no, add option, oh, there we go, add options. Yeah, so this is what I'm talking about. We can actually set options as a set of key value pairs, and these options will be build time consts, so or rather comp time consts. So we can use them. We can actually go over here to constants and set max CPU is options dot max CPU, for example. Yeah, so that's what this to do is about. Now back to where we were, virtual memory. Right, so where were we? We actually imported quite a few things here. I'm going to need to urgently clean up things. Right, so here I'm going to add. So let me think about this. We'll need a quick map page table entry, and this would be a virtual memory range. Yeah, we are going to need a range because we are going to have a few of them. And then we are going to need a quick map, which is a virtual memory range also. Right, and here we are going to init this quick map PT entry by doing something like this. So I'm just thinking for now, and this would be something like this. Right, but I think we are going to need something more. We are going to need something more. I think. So what is this about? Start the address and length and the type. So for now, I'm just going to have to set some default values. So start would be bitcast cast of 0. Sure. Length would be 0, and type would be let's call it yeah, sure, quick map. Why not? Or let's call it quick map page table entry. And let me just change this here. And this one here would need to be that. Okay, so here we are going to create actually a public function init. That returns void, and this init function here, does it return void or does it return this. Sure. So at the end of this, we are going to need to have so something like root is root for now. Levels are PML4, so let's just hardcode 4 for now, and VMM is VMM. So const root, this would be 0x1234 for now. To do read current page map address from CR3, I believe. Yeah, I think that's correct. Const VMM is, yeah, that would be that. But now we are going to go ahead and register a range in our VMM. Okay. So we probably need this register range here to also be mirrored. Oh. No, actually, hold on a minute. This is actually pretty fine. Okay. So this would solve our other issue, which is check that this is only used on initialization. That problem is solved. That problem is solved because now we can do vmm.registerRange, and we can just pass it the arguments we'd like, which are let's see here. So start would be so quick map start. Length would be quick map length. So I'm building this from the bottom up because I still have no idea how I'm going to allocate the quick map. Just have an idea in my head and I'm running with it. And args would be type is quick map. Right. Well, no. Let's not do that actually, because I already have a quick map set. So no, I'm still going to need to register it as a range. So args right. Wrong language. Wrong language again. So this is for the quick map start, and then we are going to need to also do the page table entry start and page table entry length, and this one would be page table entry. Okay, so now we just need to initialize the quick map. Right, so let's get started on our things here. So quick map start. So here we are going to need, so this is the virtual address that is fixed. So this is the virtual address that we are going to return every time we are asked to quick map something. So we are going to need to know where we are in memory here. We are going to need to decide where this address will live. And actually, one quick way to go about this is to go to our linker script here. So here we do have a kernel end symbol. What we can do is create a quick map So how do we do this? So let's align this to 4K, and we are going to create quick map, put that as no load, and we are going to but the problem here is that we don't have, or we have no idea how big this section here would need to be. So, okay, here's what I'm going to do. I'm going to cheat a little bit. Well, it's not really cheating, but so const extern const kernel end. Oh yeah, of course. Sorry. So this would be U64. Sure, that sounds okay. And this would be kernel end. And let's just, for good measure, pad that with 2 whole pages. Hold on, let me just check that my kernel end is it's not page aligned. Maybe I should page align it. Sure, that looks okay. And this would be constants, capital C, constants dot arc page size. Right, so we are just saying that the quick map virtual address will be 2 pages further away from the end of our kernel. Now the quick map length, this would have to actually be constants arc page size times our constants dot max CPU. Sure. And now let's go ahead to quick map. So pt entry start. So this one here will be a bit more involved. So let's think about how we'd like to do this. So let me just add a note here for myself. So this is the virtual address to which we map the physical address of the quick maps PTE, or page table entry. And this here, since we want it to be mapped, we could basically just choose to put it after this, but I think there's a better place for it in the higher half of the virtual address. So if we go back to main, UE5 main, so map kernel something, yeah, map kernel space. So here what we did is, this is what I'm interested in. We have this core stack address. So for every core, for every CPU of our device, we are allocating 1 page of stack just upfront. So that's what we are doing here. And all those pages have a virtual address that starts from minus 1 page. So basically that's 0x, so 4 Fs, 4 Fs, 4 Fs, and 4 zeros. Right. So, and this goes from this to 0x. So the first, so stack 0 would go from here to there, and then the others, actually, this is not right. This is right. So this one would go from this to here, oops. And yeah, so stack 1, stack 2 would go from, so E, what's before E? D. And yeah, so all the way to stack number n would be at 0x or minus page or page size, right? Times times n. So that's basically how it goes, right? And that means that we actually could choose to just set our we could do something like right after the stacks, we could put our quick map page table entry here. Probably add some padding, just 1 or 2 pages of padding, just so that we cannot mess this up. So I think that's what I'm going to do. So let's do something like, so as u64 constants arc page size, constants dot max CPU. Okay, and we are going to move that backwards by 2 constants dot arc page size. Right, and here quick map pt entry length. This would have to be so constants. I can do this. Constants dot max CPUs times the size of page mapping entry. And we need to align this to a number of pages. So stud mem align forward. So it takes a type. So u64s. The address, I don't really care. And the alignment, which is constants arc page size. Right. Actually, now that I think about this, we need to define the length first, because since these addresses are negative, they need to grow down, or rather towards 0. Yeah, towards 0. So here we need to actually do quick map pt entry length, or rather we need to subtract that. Yeah, so now that we have all of these, the only thing that remains is actually mapping this virtual address here, quick map start and quick map pointer entry start. We need to map those, and actually I think we can map them in our bootloader. We can actually go back to our bootloader and just map them right here for ease of use. But for now, I'm pretty happy with the progress that we've made. I think I formed a actually very clear idea of what I want to do. Just need to fill in the details, and that will be a bit easier now that I have a vision, a global view of where all of this is going. Yeah, so I think we are going to leave it there for now. Actually, before we go, let's not forget to do invalidate TLB for that address. Actually, for this address here, for the quick map address, const quick map address equals something, and we return quick map address. Yeah, and same goes here. We just need to make sure we invalidate that address when we finish using it. Well, that's it for this one. It was a lot of boilerplate and just thinking about how things are going to fit together. But in the grand scheme of things, this is very useful and actually primordial for the rest of the project. So, as always, if you've liked this video, leave a like, subscribe, leave a comment if you have any remarks or questions, and I'll see you next time. Fucking out.